Future engineers, subscribers, viewers, and students, there is another video in strength of materials. This is the last part, and in this video, I'm going to discuss very briefly principles and concepts on moving loads, spacing of bolts, nails, shear center, or shear distribution. So let's have the principles on moving loads, and let's consider only two moving loads, moving live loads, for simplicity in the derivation. So we have here a simply supported beam. It may be indeterminate beams, but for strength of materials, we'll have determinate beams. You can encounter composite beams and indeterminate beams in structural theory. So let's have two moving live loads, P1 and P2. And let us say P2 is heavier than P1 so that the resultant of these two loads will be closer to load 2. And we will call the distance between the resultant of the moving loads and the lighter load as X or E rather. And the distance of this point load P1 from the left support is X. And by principle, if you are familiar with the shear moment diagram, maximum moment occurs where shear is 0. So if RA is less than P1, take note that when we subtract P1, it will cross 0 shear. So the maximum moment is expected to occur under load 1. So that's why we have to derive RA. So we can derive RA, noting that the span is L by taking moment summation about B. So we have this as distance of the resultant from the right support as L minus X minus E. So summation of moment. So moment here under the load is simply RA times X. That's the anticipated expression for moment. So summation of moments about B equals 0, clockwise positive. So RA times L equals R times quantity L minus X minus E. Therefore, RA is equal to R over L, quantity L minus X minus E. And if we replace R, so we have, this is RA, so if we multiply X and distribute X into the quantities inside the brackets, then we have R over L, Lx minus X squared minus Ex. Maximizing moment by differentiating this moment expression with respect to X. So we have R over L quantity L minus 2X minus E. Then equate to 0. That means L minus 2X minus E equals 0. So that means L equals L minus 2X minus E equals 0. So that means X is L over 2 minus E over 2. If you're going to interpret this result, that means that for maximum moment to occur under point load 1, the resultant and this load should be positioned equidistant from the center line of the beam. So that means the line exactly in between P1 and R is the center line as shown here. So this should be L over 2, then this is E over 2. So that means that's the expression. That's E over 2. So for maximum moment to occur under the load, it should be positioned and the resultant of the loads equidistant from the center of the beam. So This result most probably occurs under the heavier load, and the heavier of the loads or heaviest of the loads, that's the possibility as long as uh, all the loads remain at the span. Or the other possibility by experience is when the heaviest loads, not necessarily the heaviest, but most probably when the heaviest load and the resultant of the loads are very near the center line. That's the idea, that the abs absolute maximum moment occurs under that load, under that heaviest load, when it is very close to the center. So of course, by experience and common sense, the heaviest load when very close to the center will cause great bending of the beam, and therefore that's the possibility that the absolute maximum moment occurs under it. So remember that from experience, maximum moment occurs where shear is 0. So this occurs under the point load. So that's the preliminary idea. So let's have the principles on spacing of bolts, rivets, and nails or nails. So we have here a beam. Let us say there are available um, planks, but we use those planks for economy purposes. So let us say there are two planks to be joined together by means of bolts or rivets or nails so that it will be stiffened or strengthened. So the bolts are spaced equally apart, let us say. Then the spacing would be denoted by S. And let's consider tributary area here. Let us say there's only one row of bolts or one, yes, row of bolts, and there's only one bolt. It may have two bolts just like this in this case. So this is the situation. And at the end, we have here, this is the end view. Let us say this is the shear plane where the two planks are joined, and the resistance to shear is replaced by the presence of this bolt or nail or rivet. So that this is the area to be considered in the formula shear stress equals VQ over IB. So we have here the base B, and we consider that tributary area. Let's transfer it here, and side view, of course, let's remove the solid section. It is now section which is free to slide, but sliding is prevented by the presence of the body of the bolt. So we have here the force that pushes the upper part of this plank, and it will be resisted or equated by the shear resistance of the bolt or shear or nail. So R is the shear resistance of the bolt or shear resistance of the bolt, the nail or rivet. So the shear resistance of the solid beam, which is equal to shear stress if this happens to be a solid beam, this is the idea, is equated to this shear resistance of the bolt or nail or rivet. So from the fact that that shear force is equal to shear stress maximum at the plane where sliding takes place times the area, shear area, which is equal to B dS from the figure. So it is replaced by the resistance of the bolt R. So if there are two bolts in a row, then that resistance per bolt should be multiplied by 2, just like this. So if R is 800 newtons per bolt, then the total resistance should be 1,600. This is just the demonstration. So therefore, the shear resistance of the bolt, let us say R, is equal to shear stress times Bs. And the shear stress formula, if you can recall, is VQ over IB. So replacing shear stress by VQ over IB, then times Bs, we can cancel B, then we'll have to simplify this. So R equals VQ over I times S, or VQS over I. Rearranging, and because Q is equal to area times Y, or area prime times Y, the area above the level where shear is to be calculated, or where we have here a section of the bolt or nail. In this case, since there are only two planks, and by symmetry, this is the section where shear stress is to be calculated at the neutral axis. So it is equal to that area above the neutral axis times moment arm, or distance of the centroid of that area from the neutral axis. So in general, we replace Q by AY, or A prime Y prime, then R equals V times area prime Y prime times S over I. Rearranging, S therefore equals, that's the formula, Ri over V A prime Y prime. So I read this formula as Ri over Vi, or Ri to Vi. When you want to prepare for your licensure exam, you go to, actually you can proceed to any review center. The review center does not matter, because all review centers are striving just to prepare all the students for their board exam. So the any review center does not matter. It's up to the students who prepare for the board exam. So it doesn't mean that one review center is better than the other, because all review centers are doing their job just to prepare the students to their licensure exams, respective licensure exams. So it's up to you where to have your review. But remember, the review center does not matter. It is still up to the students who will take the board exam. Because after all, if the review center, all review centers are doing well, but if the students are that poor or weak, then still the result will depend on the preparation of the students. So S is the spacing of, or pitch of bolts or nails. Then V is the R is the shear resistance of one bolt or one nail. V is shear force, the maximum shear force. Then area prime is area above the shear plane of bolts where sliding takes place. And it is also the area bounded by shear planes or shear plane. Then Y prime is distance from the centroid of area to the neutral axis of the section. So let's have the shear distribution or shear flow of beam sections. So let's have the channel section first, and the arrows would be the flow, shear flow distribution, and we multiply this by the length. So shear flow, which is denoted by Q in newtons per meter or newtons per mm, then multiply by the length. So we have here the shear, this one F, and this is also F by symmetry and equal in length also. So the vertical shear is denoted by V, capital V, and this is F. So the shear stress distribution would be, or shear stress distribution would be 0 here, then it's relatively maximum at this junction, triangular in section. So the maximum shear flow value at this junction is denoted by QF. This is also QF below by symmetry, and at the vertical web, so because we have the same point, this is also QF, then it increases, then we'll have maximum shear stress at the center, and the shear stress distribution from rectangular section is parabolic, if you can recall, or if you derive an expression for shear stress, which is area, Q is area above the section or below the section times moment arm of that area. If it is rectangular, you will notice that the resulting expression would be parabolic. So that's why this is parabolic part. And the maximum shear stress occurs at the neutral axis. So because this is parabolic and this is QF, we will denote the maximum shear stress as Qmax. Then take note that the centroid of the parabolic part is from the base is uh, from the vertex, it's 2/3 of the height of the parabola. So since the height of the parabola is Qmax minus QF, then 2/3 of that is the distance from the vertex to that point. And therefore, the average shear stress or the average shear flow would be QF plus, because the area is 2/3 base times height, where the base is the depth here, and the height is Qmax minus QF, then Q average is QF plus 2/3 of quantity Qmax minus QF. So that's the idea. This is the Qmax or tau max, denoted by Qmax or tau max. And we have here Q average, the designation, then Q is shear flow in newtons per mm, tau is shear stress in newton per mm square or megapascals. Then we have here the dimension, which is denoted by BF for the flange of the channel, and the distance between centroid is denoted by D, although the depth supposedly is the overall height of the channel. So Q average is, as I said, QF plus, because the area of the parabola is 2/3 base times height, and the base is D common, so it is equal to 2/3 of Q max minus QF. So that's the idea. You don't need to memorize. So F is simply the area of this shear flow diagram. So it is 1/2 of BF times QF. That's the expression for F. Then, of course, if we have here the moment center, then the moment of this vertical shear about that shear center is equal to the couple developed between these two forces F. So V is also equal to, this vertical shear is also equal to uh, length D times average shear flow. That's the other way of expressing that. So if that's the shear center, moment about that shear center, which is V times that distance, is equal to F times D. So that's the idea. So that's X, the distance from the web to the shear center denoted by X. So by principle, times D, F times D is equal to shear times X. So from there, you can compute X. X therefore is FD over V. You don't need to memorize, of course. You just equate the moment of this vertical shear about the shear center to the moment developed by these two F's here. So for wide flange section, on the other hand, this is the wide flange section. This would be the resulting shear stress diagram or shear flow diagram. Maximum at the neutral axis again. Then we have here an abrupt rise in shear stress or shear flow because the denominator of the formula VQ over IB is the width of the flange first, just above the junction. It is the width of the flange which is greater. Then for this abrupt increase in shear stress, the width used there is the width of the web. So that's why it rises rapidly, or it changed rapidly. These are the designation. We call this tau JF at the junction between the web and the flange, but to remember that the width of the flange is used in B in the formula VQ over IB. That B there is the B of the flange, so that's why it's lesser. Then just below the junction, the width of the section is now width of the web, so it is lesser. That's why it rises rapidly, and we'll call this tau J web to remind that it is now in the web part. And this is the maximum uh, shear stress or shear flow. And again, that's parabolic. So that's tau max. Tau max again is equal to tau JW plus 2/3 of the quantity tau max minus tau JW. So tau average is tau JW plus 2/3 of the difference between tau max and tau JW. So that's the idea. And these are the elements, BF, then tau average, then tau max, already designated, thickness of the flange, TF, thickness of the flange, and of course the depth, overall depth is T. This is the width of the web denoted by T sub W, and the depth. So next is we have to consider that that's the expression for tau max. Don't forget that. So that's it for this part of the video. So let's have this first example. The 20-meter simply supported girder of a bridge must carry 3 axle loads of a truck passing along the center of the girder, with the front axle carrying 18 kilonewtons and the rear axles carrying 72 kilonewtons each. The front axle and the middle axle are 4.3 meters apart, while the rear axles are 9.15 meters apart. So calculate the maximum bending moment due to the combined dead and live loads. Assume that the dead load is 2 kilonewtons per meter and the maximum moment occurs where live loads are positioned to cause maximum moment. The maximum shear due to combined effects of dead and live loads, and C, the maximum bending moment in the girder due to live moving axle loads plus the impact. The impact factor is given by 15 over L plus 38, and it should be less than equal to 0.3. So for the maximum moment due to the combined effect of deads and live loads, so first let's have the center load and the resultant of the loads positioned at the center line as shown. So let us compute E 162. So the maximum moment is expected to occur here. If we only consider two loads, then still all the three loads rely on the span, unless the span is reduced to, let us say, 15 or lower than that. There's a possibility that only two loads will fit in the span. So this 18 kilonewton load might be off span. So 162, which is R 72 plus 72 plus 18 times E equals 72 times 9.15 minus 18 times 4.3. So 162 times E equals 72 times 9.15 minus 18 times 4.3. Take note that the uniform weight of the beam is 2 kilonewtons per meter. So E is 3.589 meters. Then let's call this R1 and this one R2. The maximum moment is expected to occur there. Summation of moments about the right side equals 0. So R1 times 20 equals 162 times 10 minus E over 2 and plus 2 times 20 times 10 for the dead load. So R1 times 20 equals 162 times 10 minus 3.589 over 2. The distance of R from the right, R due to the live loads, then plus the moment of the dead load, which is 2 kilonewtons per meter times 20, then times 10. Solving for R1 is 86.46 kilonewtons. Then the maximum moment here is R1 times quantity 10 minus E over 2, then minus 18 times 4.3 minus the moment of the dead load, which is 2 times quantity 10 minus 3.589 over 2 square over 2. So Mmax equals 86.46 times 10 minus E over 2 minus 18 times 4.3 minus 2 times 10 minus 3.589 over 2 square over 2. So this is 2 times 10 minus 3.589 over 2. Then moment arm 10 minus 3.589 over 2 over 2. And that's why the last term looks like this. Solving for Mmax is equal to 564.7 kilonewton meter. Then the maximum shear due to combined effects of dead and live load. So we imagine that this 72 kilonewton load will be on this end here, and since we only consider the resultant, the distance of the resultant from this end would be this distance here, which is 9.15 minus E. Therefore, its distance from support 1, left support, would be 20 minus quantity 9.15 minus E. And take note, dead load is considered. So I'll call it R2 prime times 20. Summation moment at R1 is 162 times quantity 20 minus 9.15 minus 3.589, which is this distance here if the 72 kilonewton load is over the right support to cause maximum shear or maximum reaction, then plus 2 times 20 times 10. So R2 prime is equal to this, so plus 2 times 20 times 10. So R2 prime is equal to 137.0 kilonewtons. And that's also the maximum shear due to the combined effects of live and dead loads. Then the maximum bending moment in the girder due to live moving axle loads plus the impact. So the reaction here, less the reaction due to the dead load, would be 66.46. So I'll call that R1 due to live loads only. So measure moment at the right. So R1 due to live loads times 20 equals R162 times quantity 10 minus E over 2. So 10 minus 3.589 over 2. So R1 due to live loads is 66.46. The maximum moment here is 66.46 times quantity 10 minus 3.589 over 2 minus 18 times 4.3. So Mmax due to live loads only would be equal to 467.94 kilonewton meter. Then the impact factor is 15 over 20 plus 38, and that's 0.2586 less than 0.3. So that's why we use 0.2586. The maximum moment due to live loads plus the impact, therefore, is 467.94 plus 467.94 times 0.2586, or simply 467.94 times quantity 1 plus 0.2586. And that is equal to 588.9 kilonewton meter. So that's it for this video. So for the second example, a square box beam is made of two 20 by 80 mm planks and two 20 by 120 millimeter planks nailed together as shown. Knowing that the spacing between the nails is 50 mm and that the allowable shearing force in each nail is 300 newtons, determine the largest allowable vertical shear in the beam, the corresponding maximum shearing stress in the beam, and the capacity of each nail is spaced 30 millimeters apart when the vertical shear force is 1,200 newtons. So first, let's compute for the moment of inertia the outside dimensions 120 by 120. The inside dimension would be 80 by 80. So moment of inertia is BH cubed over 12, but since the base and the height are equal because these are just squares, so we have 120 to the fourth over 12, I with respect to neutral axis, 120 to the fourth over 12 minus 80 to the fourth over 12, and that is 13.87 times 10 to the 6 mm to the fourth. While we have Q at this section where the nails are present is simply 120 times 20, then moment arm from the centroid of that area to the neutral axis is 40 plus 10, 50. So Q1 equals 120 times 20 times 50, and that's 120,000 mm cube. Qmax, which is here, we add the moment of area above the neutral axis of this remaining section, which is 2 times 20 times 40 times 20. So Qmax is 120,000 plus 2 times 20 times 40 times 20, moment of these two sections. So that would be 152,000 mm cube. Formula for S is Ri over Y, Ri to Y, remember? Or A, this is A prime Y prime. This is Q1, which is 120,000. So substitute S is 50, R is 2 times 300, then V is the unknown, then area Y is 120,000. So S50, 2 times R, 2 times 300, I over V, then area Y is 120,000. Solving for V, the maximum vertical shear force is 1387 newtons. The corresponding maximum shearing stress in the beam, use VQ over IB formula, and Q this time is Q max, which is 152,000, which occurs here, the neutral axis, the maximum shear stress. B is, since the section is this, and there are two portion of the web that is cut by that section, neutral axis. So B is 2 times 20, it is 40. So substitute, B is 1387, Q max is 152,000, divided by I 13.87 times 10 to the 6, then B is 40 mm, 2 times 20. Solving for tau max in megapascals, 0.380 megapascals, or 380 kilopascals. Then finally, the capacity of each nail if spaced 30 mm apart when the vertical shear force is 1,200. So we use the same formula here. This is now 30, then 2R I over B, which is 1,200 this time, then Q area Y is 120,000. So S Ri over Y, Ri to Y. So 30 equals 2 times R, 13.87 times 10 to the 6 over shear 1,200, then area Y is Q, this is 120,000. Solving for R is 155.67 newtons or 155.7 newtons. So that's it for this video.